Welcome to Modern Study Pro. In this video, we are going to explain the second experiment, which is separation of inks by paper chromatography.
Have you ever really looked at a drop of black ink? It seems so simple, you know? Just one solid color. But what if I told you that inside that tiny drop is a hidden rainbow? Today, we're going to pull back the curtain and reveal a pretty amazing secret that's been hiding in plain sight.
So, that's the big question for today. Is black ink really just black? Or is it more like a secret recipe, a whole mix of different colors all crammed together? Well, spoiler alert, we are absolutely gonna find out.
And to solve this little mystery, we're going to set up a competition. I want you to think of it like a race, happening on a tiny strip of paper. But this isn't just any old race. It's a powerful scientific technique that lets us see things that are normally totally invisible.
Now, the official name for this race is chromatography, and at its heart, it's all about one thing: separation. We're going to force all the different parts of that ink mixture to race each other. And by seeing who's fast and who's slow, we'll uncover the ink's true identity.
Okay, so every race needs two key things, right? You need a racetrack, and you need something that gets the runners moving. In our setup, the paper itself is the racetrack. We call that the stationary phase because, well, it stays put. Then you have the liquid, the solvent, that climbs up the paper. That's the push, what gets everyone going. And we call that the mobile phase because it moves. Simple as that.
So here's how this whole race actually works. As that liquid solvent starts creeping up the paper, it's kind of like a wave trying to carry the ink colors along for the ride. But here's the secret sauce. Some colors are just more soluble. They're happier to dissolve and go with the flow, while others are a bit stickier and cling more to the paper. So the colors that dissolve really easily are like the fast swimmers. They get carried way further up the track. And the stickier ones, they get left behind. It's that difference in speed that literally pulls them apart.
All right, now that we know the rules of the road, it is time to set up our racetrack. And trust me, getting the prep work right is absolutely crucial if you want to see those cool hidden colors.
So first, we get the atmosphere just right by letting some of the solvent evaporate inside a sealed tank. Then, we take a pencil and draw our starting line. And yeah, it has to be a pencil, because the graphite won't dissolve and try to run the race with our ink. Next, we put a tiny, really concentrated dot of ink right on that line. And then we carefully hang the paper inside the tank. And just like that, the race is on.
And now we've reached what is, without a doubt, the single most important rule of this whole experiment. Your ink spot has to start above the liquid at the bottom. Why is that such a big deal? Well, if you just dip the ink directly into the solvent, it's just going to bleed out and make a big mess in the bottom of the jar. Game over before you even start. We need the solvent to climb up to the ink. That's our starting gun.
And here comes the best part. The race has started, the solvent is climbing, and we actually get to sit back and watch the magic unfold. This is the moment where that one little black spot starts to tell us its secrets.
And there it is, look at that! As the solvent moves up, it literally pulls the ink apart. What was a single black dot just blossoms into this incredible spectrum of different colors. You might see blues, reds, yellows. Each one of those is a separate ingredient from the original ink, all separated out because they ran the race at their own unique speed.
So once the solvent gets near the top of the paper, we call it. The race is over. We take the paper out right away, and with that same pencil, we mark exactly how far the liquid traveled. That line is called the solvent front, and it's a super important piece of data for what comes next.
You know, just seeing the color separate is awesome in itself, but we can actually take this a step further. We can use a little bit of simple math to give each of those separated colors its own unique identity. It's time to crack the code.
We're going to calculate something called the retention factor, or just the RF value for short. The best way to think about an RF value is like a chemical fingerprint. It's a specific number, a ratio that, under the exact same conditions, is unique to a certain compound. This is how chemists can figure out what an unknown substance actually is.
And the formula? It's beautiful. It's so simple. All we need are two measurements. First, the distance the solvent traveled. That's from our pencil's starting line all the way up to that solvent front we marked. We'll call that A. Next, for each color spot, we measure the distance from that same starting line to the very center of the spot. Let's call that B. So the RF value is simply B divided by A. That's it.
So let's say our solvent traveled 4 centimeters, and a little blue spot traveled 3 centimeters. We just calculate 3 divided by 4,
which gives us an RF value of 0.75 for that particular blue dye. See, it's just a clean, simple, and really powerful number. Now, this little RF number has a few key rules you gotta know. First, since it's a ratio, it doesn't have any units like centimeters or inches. It's also always a value between 0 and 1. I mean, a color can't possibly travel further than the solvent that's carrying it, right? A higher RF number means you've got a faster runner, a more soluble color. And most importantly, it acts like a permanent fingerprint for that specific chemical.
So we started with just one drop of black ink, and from it we revealed a whole hidden rainbow. What's wild is that this same basic paper race is used all over the real world to test for things like pesticides in our food, to identify substances at a crime scene, or even to check the purity of life-saving medicines. It really makes you wonder, doesn't it? What other secrets are out there, hiding in plain sight, just waiting for the right race to come along and reveal them?